7h20. Ok. Okay, good afternoon. So the title of the lecture is Active Glassy Systems, as was announced in the website. Um, so my name is Berthier. I work at the University of Montpellier, which is at the very south of France. So crossing to go to Les Auges was quite a trip yesterday. So what do I want to say? So maybe to introduce myself, I work on non-equilibrium phenomena of matter and a lot about disordered systems and disordered amorphous materials. So so the title is Active and Glassy. So I could do lectures, and glassy materials are a very big field. So active matter, you are the world leaders. So this is a lecture where these two fields are going to encounter and to meet, I hope, in an interesting way. So if you are a pure active systems, maybe you don't know much about the glassy. If you're pure glassy, you shouldn't be here. If you're already an expert on active glassy systems, you should be standing here. So that's the rules. So hopefully the two topics will meet. I don't know so much about active matter, so I'm very pleased to sit in front of you. And one thing I say nowadays in summer school is I remember that as a student in summer school, I was very shy. I didn't dare asking questions at dinner to the lecturers. So I realize now that as a lecturer, I'm still very shy. So I don't dare asking questions to the students. So please come and talk to me. I will be very happy to learn new physics from you guys so that I can also benefit from you. So not just a one-way thing. And also you're asking lots of questions to the lecturers already. I've seen that all day, so please continue with me. Okay, so this weekend I was trying to assemble an introduction. So I wanted to have nice movies and shows and slides and stuff. And first of all, I didn't have so much time to do it. And then something very nice happened is I was reading my email and I received a nature alert that you all receive every Friday or something. And there was a very nice paper from my introduction. So I will just quote some sentences from this paper, and that will be my introduction. Another way of introducing the topic is why do we care about glassy dense materials, the jamming transition, when we are interested in active matter? So I've looked at all the lectures you've had before, and then it's very easy to explain why I'm here. So you had all this very nice experimental work, and you hear again about these self-propelled colloidal particles. So if you start to compress and go to very large densities of colloidal systems, you'll have self-propelled active systems that will undergo some kind of interesting behavior at large densities. So that's one type of movies I could have shown you if I had the time. The other type of movie I wanted to show were probably shown by Olivier Dochot already. He has this very nice experiment with self-propelled disks in 2 dimensions. And Olivier is also an expert in glassy systems and the jamming transition. And he's now using his self-propelled hard disk to study glassy phenomena in active systems. So these are 2 movies or experiments I could have introduced. So now come this letter. So I checked this paper. So I will just quote a few sentences. And the title of the paper is called Fluid to Solid Jamming Transition Underlies Vertebrate Body Axis Elongation. So it has almost all the keywords I wanted to describe in this lecture. So most of the lectures will be really dedicated to this fluid to solid transition. Okay, so I'm just copying the keywords, fluid to solid transitions. So this is really what I'm typically interested in, and we'll be interested in this transition in the context of active matter. So that's the type of transition I'm interested in. Olivier probably showed you transition towards crystalline states, and you've heard many things about defects in crystals. I'm really interested in materials that remain disordered, remain amorphous, don't order, don't crystallize. So no crystal for this lecture, but still you can go to solid states, and this is what you have when you have window glasses. These guys are not crystal, but they are solid, and this is the type of solid that we want to discuss today. Okay. So justification for the lecture comes for the first sentence. They say that physically sculpting biological structures requires the constituent material to locally flow like a fluid while maintaining overall mechanical integrity like a solid. So that's typically the definition of glass transitions that we give when we give lectures about the glass transition. Systems that have the structure of a liquid but that have the mechanical properties of a solid. So they talk about cell assemblies that display glassy dynamics in 2 and 3 dimensions and undergo jamming transitions. So that's the introduction to the abstract. So we'll talk about glassy dynamics as a keyword, and then about jamming transitions. So these are my keywords, and these have been observed already in cell assemblies. Okay, so here they do experiments that I don't understand at all. I think they do in vivo experiments on zebrafish embryos. So that's just a tissue, like everybody else. I will use tissues the Ising model for active systems. I don't know anything about tissues, and you had the lectures by the experts before. So here they detect this jamming transition in these tissues, and they say that it explains why these tissues undergo this transition from being isotropic to being elongated. And that's the theme of that paper. So they say it's really crucial to understand the mechanical properties of these disordered assemblies, how they jam and undergo this transition to control eventually embryonic morphogenesis. Okay, so what they do typically is they do in situ mechanical measurements in these tissues, and they look at something that's called the yield stress. And this is really a big aspect of what they say. And I think Jean-François mentioned this in his first talk. That's yield stress means it's a threshold force for this tissue to start to deform when you apply a mechanical constraint to them. So if you force them a little bit, they respond as solid. But if you apply a force that above that threshold force, then they start flowing. And this is the property that these guys are measuring in situ in these tissues. So they measure yield stress, meaning these tissues behave as solids, at least on the time scales and the length scales that they probe here. And that's one thing I would like to discuss in my lectures. And eventually they go and go. The figures are super complicated. You have 19 panels per figures. But at the end, they conclude that these tissues really undergo jamming transition that's really reminiscent of what's happening in foams. So that's the analogy they make. So the analogy they have is systems like foams, where increasing the density of the particle is jamming the system. So density driven transition. And they conclude that the right analogy to understand the tissues is with foam. Okay, so I will discuss this heavily. But then they say, oh, this is an active system, by the way. So there are active fluctuations in the system. So unlike foams, of course, you have these active cellular stresses that we heard before. So what about active forces now? So up to now it was all very static, I think. But now they go to active forces, and they say, oh, this introducing lots of fluctuations. So maybe the right analogy is not necessarily with forms where the bubbles are dead because you don't have Brownian motion at all. But they say this is like thermal fluctuations. Okay. So they have sentences like this saying these active forces then make the system resemble a fluid, like a liquid. And I will discuss heavily today these dense liquids. And they say, oh, but we know that fluid to solid transitions are also observed in systems controlled by thermal fluctuations. So then they shift, and in the second part of the paper, they say, well, what we have is really a system that has thermal fluctuations. And they say, well, it has like an effective temperature. Okay, so we have these active forces, and it's really looking like an effective temperature. And then they go and they analyze the dynamic motion of the cells. So they visualize them, so you again have very nice pictures of the cells vibrating. And what they discover is the cell exhibit glassy dynamics. So I have written this here, and they say they have caged behavior. Okay, and that's something that I will mention also several times later today. So the transition from fluid to solid that they describe mechanically now is a transition from caged to uncaged. They argue, and so it goes together with the previous discussion based on mechanical measurements. So they say again it's consistent with the transition from caged to uncaged, very interesting. And then to conclude my justification why this is an important topic, they conclude with a final sentence that's really nice. They say, as suggested long ago by Darcy Thompson, the shaping of living tissues shares fundamental physical principle with the sculpting of many inert materials in which fluid to solid transitions are necessary to mold them into functional shapes. Okay, so that's just justification of my lectures, I think. So the goal of the lectures is to try to understand the words that these guys are using, try to see whether they are using them properly, and teach you how to use them properly. That's the goal. Can we define these words? So I'm not joking, these experiments are beautiful, they're probably super difficult, hard to interpret. So these guys have taken all the concepts that they could from physical sciences and from inert materials. I'm not sure they have really gone deeply into it because it's not their job, so this is our job, I think. And so what I would like to do in the lectures is try to give you insight about how to use these words properly. And maybe the main message that I want to announce is in the field of glassy disordered systems, there are many different types of fluid to solid transitions. Okay, so I will describe all these types. I think they are all related in the sense that they happen in the same materials, but they all are conceptually different, I think. They happen in different conditions, depending on the way you drive the system, depending on the type of material you're considering. So what I want to teach you is what are these types of fluid to solid transition, how they happen in the disordered systems that I know that are way simpler than the tissues. And maybe some of these concepts will be useful when you go to these very complex tissues, say, that are active and dense and disordered and behave as forms and liquids and dense systems. So that's, I think, my introduction. So, of course, ultimately, the question we want to answer is, if there are so many types of fluid to solid transitions in glassy systems, if you add activity, which type of transition is it? Okay, so the question is, when you add activity, then which type of transition do you see? Like, is it one of them, two of them, as these guys are using? They're using actually two analogies that, in my mind, cannot coexist, but they use them to interpret the experiment. So which transition, and are there new types of transition, new types of fluid to solid transition that happen only in active systems? So I hope I have time to go to these things, and what are the proper analogies with the systems that are not active? So that's the main question. So the outline for answering this question, so if I have all these words to define and introduce, I will go back to much simpler system than this living tissues. I will go to simple solids like droplets, emulsions, simple atoms, say, and we'll compress them, cool them, and see how they transform into a solid at low temperature, large densities. And that's the goal of this lecture. So today what I supposed to do is everything will be equilibrium, glassy dynamics. just to get the simple words that already exist when you don't have activities and tissues and stuff, just simple things, just to get the words right for today, and all the interesting phenomenology that already happens if you have just thermal fluctuations, pure equilibrium. Then the next lecture, I hope, will be about going non-equilibrium, because this is a school about non-equilibrium physics. I will do glassy dynamics in several types of non-equilibrium contexts, and here I will make direct connections to the lectures of Jorge Kurchen, who talked in general about non-equilibrium systems, not necessarily dense. And then, as promised, it will be active glassy dynamics. Okay, so we'll have learned sufficiently many concepts and ideas to go to active systems at the end. So that's what I want to do. Okay, and then hopefully by the end of the lectures you can go back to this paper. So maybe you could try to read it tonight, and then in 3 days you read it again and you see whether... Sorry? Well, he's probably very good then. As I said, the experiments seem to be fantastic. In the train, I realized that maybe one guy would be sitting in the room ready to punch me. So I'm not trying to make fun of these guys. I mean, if I had to write a paper on tissues, that would be ridiculous. Okay, so equilibrium glassy dynamics. So that's the... So I could do 9 hours lectures on equilibrium glassy dynamics. So what I've tried to do is select a few topics, hopefully not so many, but I think all of them may be interested in the context of active systems. So when it's interesting, I will say, oh, maybe this is interesting for active system, even though I'm discussing very simple equilibrium system. So the first thing I would like to discuss is the phenomenon of the glass transition. And the reason I want to introduce those words that don't appear in this paper is because it's the simplest fluid to solid transition just when the temperature decreases. So you take an equilibrium system, you decrease, and the system transforms into a solid. It's happening at equilibrium in the presence of the simple thermal fluctuations that we know. So the first thing that I should say that it's observed in many systems in liquids composed of molecules, or even simple molecules undergo glass transition. You would have this in polymers, and if you prefer colloids, you could have colloids and they would undergo a glass transition in equilibrium. So if you have colloidal particles that are small, not self-propelled, they undergo glass transition in equilibrium. Okay, so for a simple liquid, the control parameter that I would like to discuss first is the temperature. So you just take a liquid and you cool it down, and this is the phenomenon I want to describe. So you measure some property of the system, say it's enthalpy, energy, or volume, or density, some physical property of the system as you cool it, from the liquid state down to much lower temperature. So you follow one of these property and you start with something which is just a simple liquid. Okay, so you take water at high temperature, and normally when you cool the system, the first thing that happens that I will discard very quickly, hopefully, is the system somewhere and some temperature should undergo crystallization transition. So this is what water does at 0 Celsius. So here you have the crystal, and I won't talk about this anymore. For many of the systems, what happens is that you can easily bypass the transition and stay along the liquid branch, and you enter something which is called a supercooled liquid. Okay, so you just have a state which is metastable with respect to the crystal, but other than that, it looks like the liquid at high temperature. So if the system does not crystallize easily, you don't even know there is a crystal, and you forget about it, and I want to forget about it immediately. Okay, so this is the interesting state, so the supercooled liquid state. This is what I want to discuss a lot in the coming minutes. And if you continue cooling this guy, there will be something called TG here for glass transition, below which the system will eventually fall out of equilibrium, and it will become an amorphous solid. So this is the glass here. Okay. So this is what all figure 1s in all lectures on glassy solids and polymers looks like. So you have this liquid, it has an interesting dynamics, and I will describe this in a minute, and eventually the system falls out of equilibrium. It leaves the liquid branch to enter the glassy state, and this guy is a solid. I will show you in a minute, and this guy is really a fluid. It has a finite viscosity, and so this is the fluid to solid transition called the glass transition, and this is the phenomenon I want to describe a little bit today. Okay, so the supercooled liquid, so some people call it SL, but it's just an equilibrium liquid. So even though it has forgotten about the crystal, it's really an equilibrium material. Okay, so nothing complicated, nothing active, nothing driven here. It's an equilibrium material. So if you were there when Jorge explained the properties of equilibrium and non-equilibrium, so it has several properties. So it's time translational invariance. Okay, so you can forget about the origin of times, and your correlation functions will be dependent on just the difference of 2 times, for instance, and that was in the lectures by Jorge. Okay. The second thing that Jorge mentioned several times is about the fluctuation dissipation theorem. And again, it would be obeyed in the supercooled liquid state. So this is a statement about the relationship between response function and correlation function. So go back to Jorge's lectures and look at it. And that's a way to relate fluctuations to response that Jorge has described. Well, I mean, all the systems that really behave as good experimental supercooled liquids, you don't even know the crystalline structure. So, yes. Okay, so by contrast, the glass is not at equilibrium. So these two things then will be broken. There will be no time translational invariance, and I will discuss this in the second lectures. And the fluctuation dissipation theorem then will not be obeyed. Okay, so that's and this is FDT, so this doesn't work and this doesn't work. So these are 2 ways to test equilibrium properties, but I will tell you later when I go into the glass what properties they have. So one thing that I should say already is if you want to do this experimentally, you would cool your system here, and you would cool, and then you enter a glassy phase. And if you're an experimentalist, you could say, I will try to cool the system a bit slower. And if you do this, then what you do typically is you follow the equilibrium a little bit more, and then you fall out of equilibrium. So that guy in red would also be a glass. It would be a different glass. It will depend on the complete thermal history of the system, which is another statement about the system not being at thermal equilibrium. The state you find there at low temperature depends on how you prepared it. So it's typically a non-equilibrium state. So we have one liquid, but we have many, many glasses possible depending on how you go into the glassy phase. So that's another way to distinguish these 2 phases. It all depends on the protocol. Okay, so that's the key phenomenon. You have a system that is flowing, and then at low temperature it transforms into this arrested state, and this is how you do window glasses. Okay, so what are the key features? So this is a case where, just to mention again this analogy with the papers, you decrease the amount of thermal fluctuations you inject into the system, and the system transforms into a solid, so you don't need to invoke any analogy with forms or anything. It happens in simple liquids already. So that's another analogy that this guy could have made. Okay, so one. So some key features of the dynamics approaching the glass transition, this fluid to solid transition. And I've selected just a few of them. And again, I've tried to select the ones that may be interesting to people doing simulations or experiments or reading those papers about dense tissues. So what are the key properties that you find in this type of fluid to solid transition in thermal equilibrium? So a few things are interesting. So I have 3 of them at least. So first of all, if you look at the structure of the materials, so if you look at the structure, okay, so that's how the story goes. Typically when you do soft matter, you look at the structure and the system goes into a nematic phase. It does a phase separation somewhere. The system crystallizes, so just by looking at snapshots of your system, you recognize that the system has changed state. And that's obvious. You just show a movie and it's obvious. In glasses, the nice thing about glasses, or the interesting or non-trivial thing, is that if I give you a picture here and a picture here, the structure by the eye would look the same. And this is what's nice / interesting / complex in those systems. Just if you look, you don't see the difference between the liquid and the glass. And that's, I don't know how to write this in just sentences. It will make me ages. So one thing maybe I should do is, this is a liquid. Okay, and this is a glass. So obviously the structure hasn't changed too much. So if you want to measure, yeah, that's exactly. G of R is almost the same, exactly. So if you look at density fluctuations, so when you look at a snapshot of a particle system generated by experiments or the computer, what you do actually is you do the Fourier transform of the density fluctuations at a given wave vector. And this is what your eyes is trying to pick, large wavelength fluctuations of the density. And what Ramin discovered is just by the eye, the 2-point density fluctuations are really boring. So in a fluid, you would measure the density field at a given time. I could give its expression. Then you go to the density fluctuations in space, and then you construct the pair correlation function out of this, or the structure factor. So you could do the Fourier transform of this guy by looking at equal time density fluctuations in the real space. So it would be something like this, maybe in the Q space, delta rho minus Q T, and you do the time average, and that's the structure factor, which is related by almost by Fourier transform to the pair correlation function. And this is what your eye is picking. And when you look at systems close to the glass transition or below or above, this guy almost doesn't change. Okay, so very, very small change as T goes to Tg, and even into the glass, the system really hasn't really ordered very much. So that's the sentences in the opening of this paper, that if you look at the system here, it has the structure of a fluid, but mechanically it's behavior as a solid, and this is what this statement is about. So you've understood the first sentence of the paper already. So some people say the structure then is boring, and I think the whole question is how boring, and what in the structure is really interesting, and that's a whole well, because it has a small temperature evolution, because the amplitude of the vibrations are changing, so the peak is sharpening just a little bit. No, So the only thing you see is that if you follow some quantity, then it will fall out of equilibrium. So you may have a kink in the, say, the first peak of Java or something, but it's just reflecting what you see in the energy, nothing else. Okay, so that's the statement about the structure. It's boring, it's not changing very much, but in like a few minutes I will say some theories are built entirely on these tiny changes of Java. So how boring this is, it depends on who you are in that field. Okay, so that's the structure. Then I go slowly. If I look at thermodynamic properties, so that was the pair correlation function. Thermodynamics, again, many things are changing very smoothly across the transition, but there is one quantity that has been discussed in thousands of papers that's called the configurational entropy. So we'll just say a few words about that because it relates to some theories, and I think as a concept it's interesting. Okay, so the configurational entropy in the experiments dedicated to these supercooled liquids, the way it's defined and measured experimentally, it's like this. So this is the configurational entropy, and so experimentalists would measure at a given temperature the entropy of the liquid. So they would do some calorimetric experiments to measure the entropy of the liquid, looking at the specific heat and stuff. And from this, they would like to subtract the entropy of the crystal that they don't forget for 5 minutes at the very same temperature. And the idea they have in mind is in the crystal you have just these crystalline ordered states and you have small fluctuations of the particles. And they say these small fluctuations are giving very trivial contributions to the entropy, just the entropy of vibrations near one state. So you remove these trivial vibrations by removing the entropy associated to how many states you have near one given configurations. And this is how they define the configurational entropy. It's been measured in tens of supercooled liquids. So I just give you a cartoon of how it looks. So again, how you draw the cartoon also shows what's your idea about how important that is. So what they do is, typically experimentally, they would measure sconf, and they would normalize by the value of sconf as some reference temperature high into the liquid. So you would take T star somewhere here. Somewhere where the physics is really boring, it's just the liquid, just a reference state to normalize things. So by definition, that point here would start. This would be 1 and this would be 1. So the question is how much does the entropy decrease as you decrease the temperature, and experiments look like this. Okay, so this is where you show how strongly you believe in thermodynamics. So that's experiments, and of course in the experiment you reach TG here, so the system falls out of equilibrium, and then you cannot measure the entropy, the configuration and entropy lower. Okay, so that was shown in a paper in 1948 by some guy called Kotzmann. Okay, so who compiled tens of experimental works on this, and he said, well, that's strange because this configurational entropy is changing quite a bit as I approach the glass transition, to the point that if I were to extrapolate this to low temperature, if I just take the data like this, it seems that there is a temperature that's now called the Kaufman temperature, where this configurational entropy maybe would vanish if this behavior persists. So nobody knows, of course, and nobody knows since Kaufman whether this extrapolation is true or not. But at least there is this idea that maybe somewhere there is a temperature that's clearly not zero if you extrapolate, where something interesting could happen in the thermodynamics. And because the entropy goes to 0, it has received the name of an entropy crisis. Okay, so that's the idea of an underlying phase transition to the glass transition. And so really what this phase transition would be about would be saying that as I decrease the temperature, the number of states that the system can find is really decreasing. It's decreasing too much that at TK there are no more states available and the system is just frozen. So that's the idea that the rarefaction of the number of available states is driving the glassy dynamics. So that's, of course, still an open question in the field, but I think it's a big, interesting open questions. Yep. It's an everything I say today is equilibrium, so you'd need just enough time to thermalize the system, but when it's done, it's non-controversial how I measure it. It's just the good old entropy at thermal equilibrium. So what was your question? You didn't finish your sentence. Well, they do calorimetric measurements by going up and down and measuring the specific heat and doing integration. So it's nothing really dramatic there. No, it's really equilibrium measurement. So what would depend on time is what you measure below Tg, and here that would depend on specifically how fast you went, how long you waited, ta. But today, as I said, it's pure equilibrium. So what we don't know is how to go into really the low temperature, how to extrapolate this, we don't know. But at least as long as you're thermally equilibrated, it's all well defined as a measurement. Yes. In principle, you're right. It's just a matter of in practice, and I'll give you the quantitative answer to as to why this is good in principle but impossible in practice later. Okay, so that's the idea that glassy dynamics may be really driven by the structure that the system can find and how difficult it is to assemble these particles at low temperature. So when you go to the soft matter community, usually this part about the glass transition, it's not discussed because it's too complicated, I think. So as a concept, to do an analogy, the configurational entropy is never used, even though I think it's really driving a lot of the physics and it's interesting. In the context of active, I think nobody has tried to think about configurational entropy, but I think it's as good to say, well, it's caged and caged as saying, well, there is less configurational entropy, but this analogy is never made, presumably because entropy is, as we know, a difficult concept. I will show you how it goes when you have a real transition, because there are models where it goes, and hopefully I will be able to answer your question. Yes? It's not defined. As I said, I mean, if you call, differently, then you find a different answer. So how do you define it rigorously? Something that changes if you start to. So you cannot define it rigorously. So what people do is they have some, empirical, physically justified criterion, like when the relaxation time I measure like this or this crosses 100 seconds, this is TG. That's it. You can do tens of different types of measurements, mechanics, thermodynamics, microscopic dynamics, how particles move, everything will give you some TG depending on what criterion you then you decide to apply to your measurement. But as a phase transition, it's not well defined. It's just a simple crossover where your system falls out of equilibrium for practical reasons. That's all. Yes, that's all. So what I'm saying is that everything in the glass phase depends on everything. But today I don't want to discuss the glass, I want to discuss the equilibrium liquid, where by definition it does not depend on how you went there. Just wait long enough, you thermalize, and then you start your measurements. That's all. Okay, that's simple for today. So that's thermodynamics. So it's kind of interesting but difficult to grasp, and I should probably say already, difficult to apply to non-equilibrium systems, because how do you define configurational entropy out of equilibrium is a question that I have in my mind. But I think it's interesting. So what is really spectacular and that people like to describe is the dynamics, and this is where all these analogies with Glassy systems, I think, are appealing to experimentalists and people looking at how the particles or the tissues are moving. The dynamics is really spectacular. So we talked that in the statics you can look at the Fourier transform of the density-density correlation functions. If you want to look at dynamics, you have to look at time correlation functions. Okay, so I'm just writing them to have a few specific examples of quantities that you can measure. So people in liquids would really look at the time analog of this density-density correlation function. So the only difference with the static structure factor is now that I'm looking at density fluctuations at different times, and this is in the Fourier space. Okay, so this is one type of well understood analyzed measure, and it's really looking at how the density fluctuations in that liquid are changing as the liquid is reorganizing. So maybe to make the connections with some of the measurements or experiments that you've seen. So it is not, again, a very simple quantity to measure if you just look at particles in your microscope. So maybe I should. So if you think of the density field in terms of its microscopic expression, in terms of delta functions of the positions of the particles, this then takes a very simple form in the Fourier space. It would be something like this. Q times Ri minus Rj of 0. And that would be something like this. So this is the microscopic expression in terms of the positions of all the particles as a function of the particle trajectories. This is the microscopic expression of this. So it's called the intermediate scattering function in the jargon. So one quantity that people like is the self part of this guy. And I'm just trying to go to the quantities that you have seen before. So the self part means that in this double sum over I and j, I just take the equal terms here. So what you have is something like this. So you take your particles in the microscope, you look at the displacement over a given amount of time, you compare this to a typical wave vector, you take the cosine, So this guy goes from 1 to 0 when the typical particle displacement is larger than 2 pi divided by q. So it's called the self part of the intermediate scattering function. And if you think about the q going to 0 limit of this, so large scale displacements, you will develop the exponential, so you'll have a 1 plus iq something, which on average will come to 0. And then you have the square term, and the square term will be simply the mean square displacement that you've heard about in all the lectures before. So one quantity that people really like is something like this, which is just RIT minus RI0 squared and then average. It's just telling you how fast the particles are moving. And this is how we look at the dynamics in these dense systems, and mean square displacements you find in this Nature paper in one of the panels of figure 2. And so what I'm about to show you is that the dynamics at the single particle level in this system is really changing spectacularly. So this is the mean square displacement that everybody in doing confocal microscopy or direct observations on granular and colloids is really measuring. So let me go back to time correlation functions because I like them better. And this is how a typical time correlation function look like. So I like to use log scales because these things are going to be very slow and relaxing on many different time scales. And I'm looking at time correlation functions that go from 1 when nothing has moved to 0 when the structure of the system has relaxed a lot. So by definition, 10 log goes to minus infinity at short times, and that would be 1, that would be 0. And this is, again, as a cartoon, what a typical time correlation function of a system approaching the glass transition is looking like. So it has this funny two-step decay, and if you go to lower temperature, then you have a slower decay here, and if you go to an even lower temperature, then you'll have an even slower decay here. And so this is as temperature decreases. So what you should see is you have a two-step. Let me describe it, and then I take the question, please. So what you have as broad features, and then I answer the question, is you have a two-step decay. So you have something fast happening at short time scale that doesn't depend very much on temperature. So this is short time dynamics. Then in log scale, you have a long plateau. So the particles have done something, but then they stop moving. And finally, you have the slow relaxation. Okay, so this is what this two-step decay is about, and the fact that you have this plateau is really this caging effect that these guys were mentioning. So the particles are doing a little bit of vibrations, so you have imperfect correlations, but the system is still frozen, and at much larger time scale, this can be orders of magnitude longer. Finally, the particles can move and rearrange the system, and you have a relaxation of the structure of the liquid, but these are two well separated things. So this plateau is what these guys have called caging. Okay, so now I can take the question. You still? Well, CT is just a generic name for one of those time correlation functions. Okay, you can look at stress correlation functions. Everything will be looking like this because this is what the particles are doing. They do some kind of thermal vibrations, and then finally they find ways to relax at much longer time scales. I think it's a name for having in your time correlation functions two-step decay well separated timescales for slow things and fast things. Okay. So how do you define the it's can you see a plateau in log? Like, do you see two types of relaxations? And if you go in the high temperature fluid, I should have said before, you would see simple mono exponential decay, and so the particles just flow wherever they want at very fast speed. So what this caging means is that you have these vibrations that are well separated. So I think in soft matter they would call it maybe viscoelasticity. It would be solid at short times and liquid at long times. So it's a separation. It's a statement about separation of time scale. So well, I forget about that. I mean, what it means is this: that if I show you a movie that stops here, the particles will look arrested. If I show you a movie at much larger time, they will flow and diffuse. So the details of this, I think, don't matter for today's lecture, I think. Okay, so different things. So people have talked about the form of these correlation functions. I just give you the name because presumably in some papers it will appear. So if you look at the time dependence of that thing, it behaves like this. So it's not an exponential thing, it's called a compressed exponential. So that exponent is smaller than one, it's called a stretch exponential. And then there are dozens of papers trying to quantify this beta, discuss its physical meaning that I don't care for today. Just saying that it's a broad distribution of relaxation time. That's all I need for today. And presumably if you go to active systems and colloids and stuff, you will find stretch exponential decay like this. So broad distribution of relaxation times. So what's more interesting is what's the temperature dependence of this relaxation time. So you have a relaxation time tau that depends on temperature, and obviously from my cartoon, as I decrease the temperature, the relaxation time increases by orders of magnitude because it's changing in log scale. So again, dozens, tens, hundreds of measurements of this relaxation time. So for simple liquids, this is how the cartoon looks like. And people like to plot it this way. So they plot the logarithm of the relaxation time because it's changing by orders of magnitude. So you have to take the log. And then people show it as a function of the inverse of the temperature. And the reason is that if you have an Arrhenius dependence of the relaxation time, you'll get a straight line here. Okay, so log tau would be proportional to 1 over t, that would be Arrhenius. So anything non-Arrhenius will show in this plot. So that would be Arrhenius activated dynamics over a single energy barriers, and the measurements, I don't know what color I could use, do follow this Arrhenius behavior up to a point, and then they explode dramatically. So again, it's a cartoon. The reality maybe sometimes is a bit different, and the numbers are interesting. So if you think about molecular glassy systems made of atoms, so simple liquids, so in log scale this would be say -12 here in seconds, so that would be of the order of picoseconds. And when you reach Tg here, and it's really tough to do measurements because it requires waiting and be patient, this guy would be 2, and that's in seconds. So it means that here you have 14 decades. Okay, so that's why I'm saying the dynamics is spectacular, is that you decrease the temperature, you approach the glass, and you have all these things happening. You have this two-step decay, this caging, and this very fast increase of the relaxation times. So if you do an experiment with colloids where your microscopic relaxation time is not picoseconds, but say milliseconds, and you can observe them and do light scattering up to, say, I don't know, 1000 seconds if you're patient, you'll be able to observe at best something like 6 decays, and then the decay of this correlation function will be so slow that you will measure something that never decays like this. If you do experiments on much bigger particles because you want to do confocal microscopy, so you go to 1 micron, so the microscopic timescale is already, say, 1 second, and your patience is about 100 seconds still, so you see 2 decades. So it means that the bigger and the larger, the more complicated the system, the smaller the range of the dynamics you'll be able to measure in a typical experiment. But for the molecular systems controlled by temperature, we have all this range where these interesting things happen. Okay. So the key thing, and this is where, is that this is obviously faster than Arrhenius, so it's called super Arrhenius. Okay, so it means that if you want to think in terms of thermally activated events, so you have an activation energy and then the system has to cross these energy barriers, what you need to introduce is the idea that the activation energy you have itself, it's growing as you decrease the temperature. So the apparent activation energy grows when the temperature decreases. So because you always talk about some kind of active matter and collective motion, this is also what we do in this context of glassy dynamics. We say, oh, as we decrease the temperature, the dynamics slows down because larger things have to move. So motions have to become collective. So in a sense, attached to this idea is the idea of collective motion. That, again, people working on tissues have discussed a lot as an analog to glassy dynamics. I will make this analogy in a minute. Okay, so that suggests, just by these simple functional forms, the idea that the dynamics become slow, interesting, caged, two-step, broad distribution of relaxation times, and probably increasingly collective as you approach the glassy state. So it's interesting in a sense. Okay. So I could probably skip this to go a bit faster. So what about this idea of collective motion, and what's known in the context of glassy systems? And again, it's a whole chapter in the business of glassy materials. So the idea that motion is spatially correlated, which is what you think in terms of groups of particles moving together, it has received a name, and the name is called dynamic heterogeneity. And really the idea behind this is really to quantify this empirical a notion that the particles have to move in a correlated manner to relax the structure of the liquid. Okay, so this is how it goes. I will give you just one definition of a typical length scales to quantify this collective motion. So the goal of this is to extract a length scale for, so I'm using your jargon now, for collective motion. Okay, so we don't use the word the collective motion, but you like it better. So what I have in mind is really what people do when they watch tissues again moving. So you take your particles. So this is the snapshot at time 0. And it's again looking like a boring GeoVar. But now you keep the image moving and you look at the movie and not at the snapshot. And for each particle, you would record the displacement over a given amount of time between 0 and t. So if we want to understand how the system relaxes its structure, what we would do is look at the displacements when the system is about to relax. So we would look really at the time interval, so t is between 0 and the relaxation time. And if you're lucky, you can watch all the particles, or you do computer simulations. And for each particle, then you have access to something which is what I draw before. So this is the displacement for each particle, which is resolved both in space and time, because you really observe the movie of the particles. Okay, so I said that from this quantity you could define the contribution of particle I to my correlation function. So that was something like this. So I'm just rewriting one term in the sum that I described before, but now I don't have the sum of our particles and I don't have the summal average. It's just for this particle in this movie, this is the contribution to the correlation function. So of course, if I measure the average of this guy, then I go back to my normal time correlation function that would have this behavior like this. But now I want to do more. I don't want to ask questions about the average. I want to ask questions about the special correlations between groups of particles that have relaxed together. So I'm asking the question, is the displacement of this particle, this particle, this particle, this particle, is it correlated in space? What I want to look is, I want to look whether each particle has the same displacement correlated in space. So the type of quantity that I would like to compute, and I just write the expression for the sake of it, would be like, so we call it G4 in the jargon. I don't know why it's green, because you can't see it very much. So it's really something that looks like the pair correlation function, but now it's weighted by this dynamic function. So it would be something like delta R minus Ri minus Rj, something like this. Okay, so if you forget about this quantity, this is almost the definition of the pair correlation function, so density-density correlation. If you weight now the position of the particle by their displacements, what you have is special correlations between the displacements of two particles. And now you do the average of that quantity. And then it's telling you how big are these domains. Okay, so that's the goal of all this game. So from such measurements and their generalizations in Fourier space and experiments, it's about 20 years of work in the field of class physics. So the one conclusion is that so if you look at how this thing decays in space, you could extract a correlation length that, for reasons that are difficult to understand, is called Xi4. So this is Xi4, a dynamic correlation length. That quantifies how big are these domains of correlated particle motion. And this has been measured directly or indirectly. And this length scale is growing, let me say, significantly. as the temperature decreases towards the glass transition. It's not dramatic, but still it's bigger than any other lengths that people have been able to detect in those systems. So in a sense, what we are saying by these statements is that the system is slowing down, the particles are caged, and to escape their cages, they have to move in some form of correlated manner. So that's a form of collective motion, if you wish, that dense systems would have to perform in order to relax the structure when they are very dense. So you don't need to be jammed or have soft modes or be out of equilibrium or driven by active systems. Just systems at thermal equilibrium have this. And I think the deep physical reason is when you're dense, if you want to move, then you have to move with your neighbor, and that's it. I don't answer that question. Yeah, so that's okay. So the reason why I can't answer your question is nothing is diverging, because what I said is the experiments are going on and then they stop at TG, and that's it. So by definition, nothing is diverging because you can never approach any of the singularities that I mentioned, like TK or something. So you do whatever you can do in the experiments and then they stop. So the question is, if you try to extrapolate what's going to happen, is the time diverging, is the length diverging? And these are unanswered questions, and questions that presumably cannot be answered experimentally. That's why I'm not giving an answer. Another question is, I skipped that part actually. So if we think about the connection between correlated motion and energy scale for relaxation and relaxation times, the way we think about it in these systems is that maybe the energy scale to relax the system, so it will be depending on how big are these domains. And I don't know, people have invented models, or you have theories of approximations for this, and I don't know. We like to introduce some exponent relating how big are the domains to how big is the energy barrier with unknown exponent. Say D, for instance. D would be you relax the volume. Okay. So let me put D. So you take a bunch of particles, and the energy barrier is the price to pay to relax everybody in that volume. And now, because this is activated energy, we believe that the time would be something like this. So exponential of E divided by kBt, so that would be something like this. Okay. So that's not well established, understood, but how we think about it is you have a small growth of the correlation length, then you take the volume, but you take it in the exponential, the time is exploding like this. That means a modest growth of this correlated motion is enough to give you these 14 decades, because actually the interesting quantity is this or this, and it's changing between minus 12 and 2. It's not changing by 14 decades, it's changing by just 1 decade. Okay, so that's an interesting question, thanks. So in the introduction to the Nature paper, they say, glassy dynamics has been previously observed in cell assemblies. So one paper that maybe you know, it's a PNAS paper from, I never remember, 11 or 10 by Angie Lini et al. One of the et al. Is Dave Weiss, I think. And in this paper, they have carefully measured something related to correlated motion in these dense tissues. And the analogy they make in that paper is really with this dynamic heterogeneity that people see in dense colloids or supercooled liquids. So this is the analogy that's made in this paper. Even though if you look at the experiments, what they measure is really a velocity-velocity correlation function. I think they look at displacement at very short times, like the shortest times they have to resolve the displacement. So it's like a velocity-velocity correlation function. So of course, if you integrate the velocity over time, you will get the displacement. But it's unclear to me whether what they see is really the same as the structural relaxation that we discuss in supercooled liquid as compared to velocity-velocity correlation functions. I think I'll try to make that point a bit later when I go out of equilibrium. if you think about a liquid at a thermal equilibrium and you think of velocity-velocity correlations, there are none because the velocities and the positions decouple in equilibrium. That's the Maxwell-Boltzmann distribution. So this does not exist in an equilibrium system. Okay, let me think. So we stop at 20, 25. Okay. So these are the key ideas. So time, length, dynamics, structure, thermodynamics that may be useful and are used already as analogies. A little bit about theory of and models and some theoretical ideas. And I'm introducing all of these because then if I want to go active, there will be the active Glassy systems that I will discuss in the final lectures will be slight modifications of this. So I spend a little bit of time to gain time at the end. That was a question. Yeah. Yeah, so you should, yeah. So some people in that field like Greek letters, so introduce energy scales and stuff, and then of course KBT has disappeared and everything. But you should make this an energy and then divide by KBT. Oof. I don't know. It's too complicated to answer today. I think people are fighting about this, whether this scale should be finite, increasing, decreasing, and what scale is it and how to measure it. So what I wanted to convey as an idea is the answer to his question is what's typically the relation between length and time in supercooled liquid. Then the details of these relationships are not known. Okay, so if you want to do theory and models, then what you have to do is define a simple model in terms of the interactions between the particles and then give them some dynamics to study caging and glassy dynamics and activated correlated motion and stuff. So what you need is to study equilibrium dynamics for interacting particles. Okay, so I'm just saying something really stupid. So what I want to talk about is two things. So what type of interactions do you consider in the simplest cases that I will also use for active systems? And what type of dynamics do you use again to have it ready to go active at the end? Okay, so the simple thing that people do is they say, oh, the Hamiltonian is the sum of pair interactions. So you're saying something like this, okay? So we take pair interactions. And we take point light particles. So I'm just doing, liquid state theory in a sense. So the canonical model in our field, I want to write it because I will use it in a minute, is so for the pair interaction, people come from the liquid state theory from the 70s and they like the Lennard-Jones potential, which has this functional form. And there are maybe thousands of computer simulations and theoretical calculations done with the Lennard-Jones potential. So it's a canonical for interacting liquids, a canonical model for interacting liquids. I keep losing this. Okay, so you have this very steep repulsion at short distances, and then you have a longer range attraction at large distances. So this is how the Lennard-Jones potential one looks like. So let me draw it. So I said this is sigma, so you'll have a very steep repulsion here, and then a longer range attraction here. So this is the R minus 12, and this is the R minus 6. Okay, so this is typically the type of system that we like. So let me insist a little bit on control parameters, because again, It's something I like to do when I go to the active system. So when you take a fluid like this, the control parameters you'll have will be temperature and say density. So you have two control parameters. You fix the number density, so how many particles you put, and then you change the temperature. Or equivalently, you could control the pressure, but it's really the same thing. Okay, so that's the canonical liquid that we like to study, and I will come back to models that you are more familiar with in the context of active system. So that's the interaction part. So this is how particles interact. So now about the dynamics. And I think it's a little bit interesting, and I think it connects to things I'm going to repeat many, many times. So if you want to study atomic liquids, typically you would study Newtonian dynamics. And molecular dynamics simulations for supercooled liquid typically solve Newton's equation. This is molecular dynamics. Okay, so you have, for each particle, you need to solve this, and this is the sum of all the interparticle forces. Okay, so we don't care too much. So now came the physics of colloidal systems into the game of the glass transition. So people have started to look at Langevin dynamics. And this is the type of dynamics that Jorge has discussed a lot. So you add the dissipation and thermal noise to your equation because you think of big particles in the solvent. So the way I'm going to change this, I think it really doesn't matter too much, but you have a friction term that I write like this. And then you still have your forces, but now you add friction. You had friction and the random noise. So this is the Langevin dynamics that Jorge has discussed a lot. And of course, the time correlation functions of the noise have to be related to the friction constant for the system to go to thermal equilibrium. So you have something like psi of t prime, and I forget about all the indices here, but it's uncorrelated noise. So it will be 2 gamma kt and delta functions of everything, in particular the time t minus t prime. Okay, so that's the statement that the thermal bath itself is at equilibrium. If you go to really overdamped dynamics, you can kill this, and this is how Jorge was doing the calculations. And there are tons of simulations and experimental realizations of Brownian and Langevin dynamics in the context of Glassy systems. So I do computer simulations. I'm just describing Monte Carlo simulations just to surprise you in a minute. Okay, so I like to do Monte Carlo simulations of these dense systems. So you put your particles in the computer, and the way you can simulate these dense liquids in Monte Carlo simulations is as follows. So the algorithm is really, really stupid, and that's why I like it. Is you take one particle at random, you try to give it a little kick. Okay, so you take particle I at random, say, then you try to give it a little kick. So you propose a displacement delta I, which is again random number. So you have a 3 vector components. That's I don't know. So you have delta x, delta y, and you say I pick a random vector that's not too big, otherwise it's impossible, not too small, otherwise it's then you compute the energy chance that moving the particle is going to produce. Okay, so that's Monte Carlo simulations in one line. Then you say, oh, I have to respect detailed balance. That was explained by Jorge Cochan again. And then you say, I have to accept this Monte Carlo move with some probability that respects detailed balance to lead to equilibrium. I accept or reject, and then I restart. I take another particle, try to move it, accept, reject. So the point I want to make and the joke I want to make, it's a super unphysical dynamics. It's not a dynamics that real particles would do. You just try moves and you accept and reject. No, you try to move it. If there is someone you reject, because the energy cost will be too large. You don't look, you propose at random, otherwise you will break detail balance. Exactly. No? One by one. That's why I'm saying it's stupid. It's by stupid I mean unphysical. No real system would move the particles one by one sequentially like this. But if you respect all the rules of detail balance and equilibrium, the system is going to probe the very same equilibrium configurations as everything else you did by the physical dynamics. So by definition, statics and thermodynamic properties are preserved by this algorithm. But the remarkable result that I'm about to expose. So again, I should insist, because this all respects the rules of equilibrium, you'll have the same thermodynamics and static properties. But the result is that if you look at the dynamics, then the result is the short-time dynamics really depends on the macroscopic rules. Okay, so the caging, the short times, it does depend on the macroscopic rules. But if you look at the long-time dynamics, it does not. And that's a result that you wouldn't have been able to guess, because I told you it's very unphysical. But if you do this and you measure the relaxation time and you plot its temperature dependence, it will be very much the same as the Newtonian dynamics or the Langevin dynamics. So it means that if you look at the temperature dependence of Newtonian dynamics or Langevin or even Monte Carlo dynamics, all these things, they have the very same temperature dependence. So, and that's one of the key ideas I would like to tell is that because of this separation of scales between what's happening at short times and the time it takes to build the structural relaxation orders of magnitude slower, the details of how you're moving your particle are short distances, short times, they don't matter at all. The system will take the same route to move whatever the macroscopic dynamics. And that idea of the separation of time scale is then resulting in a separation between the details at short times and what's emerging at long times. It will be a theme of these lectures. To try to do. Yes. 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 You're right. Yeah, but I forget about the crystal all day. Well, no. Okay, so that's a more precise question. So the ability to study the glass transition in, say, a computer simulation relies on building interactions in a specific microscopic model that doesn't easily go to the crystal. Yeah, so we have plenty of models in the literature where nobody knows the crystal because it's so difficult to find that you don't find it. Never, even if you do Monte Carlo things. So what you keep exploring is the metastable supercooled liquid state without finding the crystal. What do I want to say today? Okay, phase diagram rapidly, because that will be useful. Okay, so I say the two control parameters are temperature and density. So typically you find a line or glass transition that's like this, where you would have the liquid and you would have the glass. And because this is a system that has attractions at low density, you'll have a liquid gas phase separation, but that's a really low density. So we're interested in the glass transition as you decrease the temperature and you enter the glass. And this is how the phase diagram would look like. So notice, by the way, that if you compress the system like this, you can already enter the glassy phase just by increasing the density of this. So in a sense, there are many routes to go from the liquid to the glass, even at equilibrium, without calling this an analogy with forms or everything. Simple liquids can get arrested because the density increases. So a very popular model for active systems, and that has been mentioned in the lecture this morning, is this Weeks-Chandler Anderson potential, WCA. And for whatever reason, this is the model that everybody has picked up in the field of self-propelled particles. So it's based on the Lennard-Jones system, but it's like this. It's the very same potential up to the minimum here, but then you don't include the attractive part. So you say up to here it's the same functional force, but here I make it constant. And because you don't like this large constant, then you shift the potential to 0. Okay. So this is the WCA. So at short distances, it has the same functional form as the Lennard-Jones, but at distances larger than this cutoff here, you remove the attractive part of the business. So it's a nice model because you remove the attraction between the particles, you kill that part here. So the liquid gas phase separation disappears. So for the WCA potential, I really like this temperature density phase diagram. You can follow this arbitrarily low in densities, and this is the result. So this is how TG depends on density, and you don't have this liquid gas phase separation at low density. So there appears an interesting density here where the glass transition seems to be going to 0. And this is the phase diagram for then the WCA potential. And this one would be for the Lennard-Jones, where you cannot really access this without demixing between the liquid and the gas. So that's an interesting question to ask, what's happening here, and I will answer that question. So what about the t going to 0 limit in that thing? So what's happening? Why is it that this liquid, and this is the glass, and so what's happening as t goes to 0? So you should remember that we started from an interaction potential that had an epsilon in front of everything. So there was a hidden energy scale. So when I say the temperature goes to 0, what I'm stating is that t divided by epsilon is going to 0 actually. So one way of thinking about this limit is by saying, well, I keep t constant, but I send epsilon to infinity. So if you think of sending the epsilon to infinity, you will be making this steeper and steeper and steeper. So sending epsilon to infinity is like studying this pair potential. That would be infinity below some threshold and 0 above. So in that limit, actually what you're doing is you're simulating what's called the hard sphere potential. Okay, so that's the reason why the WCA potential is so popular in a self-propelled system. That it's almost like a hard sphere potential, but it's soft, so it's simpler to simulate and analyze. And that's the reason why. And so what's nice about the hard sphere potential is that it's so steep that the amplitude of the thermal fluctuations don't matter anymore. So instead of having 2 control parameters, you have just one. And your one control parameter is the density. So you have a fluid that goes into a glass as the density increases. So the glass transition of hard spheres, it's a one-dimensional phase diagram. This is why I like them very much. So the phase diagram of hard sphere is just a one control parameter thing, which is the density, because the thermal fluctuations don't matter anymore. Well, it's machinery of computer simulations. So the answer is no, and the reason is we want to avoid crystallization. So we want to make it hard for the system to crystallize. I don't know who asked the questions. Okay. So what we typically do is we take mixtures of particles with different sizes. So these guys, to crystallize, would have to invent presumably a very complicated unit cells, and they don't find it in the computer. So it's just a trick we use to kill and forget about the crystal. But it's a detail apart from this. Okay, one parameter that I want to mention is spatial dimensions. And this is how presumably I'm going to end very soon. So if you think of hard spheres in one dimension, it won't be very interesting because the particles cannot cross each other. However, if you look at 2 dimensions, it's already interesting, and there are many colloidal experiments that are done in 2 dimensions. Of course, we live in 3 dimensions. Simulations in 4 dimensions are possible. Experiments become very hard. Then we go to 8, and then we go to infinity. Okay, so that's what I said. So there are experiments performed in 2 and 3 dimensions in these glassy systems, and of course 2 dimensions is really where active systems are studied. So the tissues are 2-dimensional, the particles sediment in 2-dimensional space in Lyon, for instance. The liquids are studied experimentally in 3 dimensions. Simulation these days have been pushed to 8 dimensions. I'm working with Patrick Charbonneau, who will be watching the lectures, I'm sure. So you can do simulations up to 8 dimensions to study whether larger dimensions simplify or complicate the problem, and this is where simulations have been done. And of course, we can't do simulations in easily in infinite dimensions, but this is where theories of the glass transition, it turns out, become available. Okay, so going to large dimensions means that you're doing a mean field theory of your liquid. So this is the this is where the mean field theory of the glass transition lives. It lives in infinite dimensions. So what I mean by this is that quite recently, a few years ago, the people in the group of Jorge Corchan and Francesco Zamponi in Paris and Giorgio Parisi in Rome have been able to develop this mean field theory of the glass transition by going to large dimensions with any of the pair potentials I mentioned before. So you take a Lennard-Jones hard sphere, a Berthier something, you just take the limit of large dimensions, and there you do no more approximations. You do an exact statistical mechanics calculations, and you derive what would be the behavior in large dimensions of these liquids. So this is where the mean field theory of the glass transition exists. I will say a few words probably next time about that mean field theory. So these were models for liquids, and I want to connect a little bit to a few things that Jorge has said before. I should say like this, the field of the glass transition, it's big. I'm not entering any of the heated discussions about what's the best theory of the glass transition in the world, but there are many available. And in particular, there are more abstract models to describe glassy physics. And this is how I'm going to end for today. And more abstract models means you go to the lattice, you introduce spin models, funny interactions, whatever. So there are tons of them. I will mention just one because I'm sharing my lectures with Jorge, so I have to. So imagine that you have spin models. Okay, so you have interacting spins, could be on the lattice, could be anything. So let me construct the abstract model like this. So you have a minus if you want, then you have a sum of, say, pairs of neighboring spins like this. And that would be just the Ising model on the lattice with nearest neighbor interactions. So there are many things you can move out of the Ising model. You can go to multi-spin interactions. Okay. So the experts know where I'm heading. So you can introduce, for instance, plaquette interactions, 4 spin interactions on the lattice. So that's going multi-spin. You can introduce quench disorder, so you would have interactions that depend specifically of which quadruplet of spins that you do. So this is quench disorder. So what you've now instead of having a model for the ferromagnetic transition, it's a model for spin interacting with disorder. So it's a spin glass model. And if you want to connect with the mean field, then you say, I'm going to remove this and sum over all possible quadruplet of spin. So you take the mean field limit. Okay, so if you take the mean field limit, so I don't know how to put colors for erasing something. Okay. So take the mean field limit of everybody interacting with everybody. Okay, so what you have is a very abstract model of spins interacting with quench disordered interactions, and everybody is talking to everybody. So it's called the four-spin spin glass. So it's a model of mean field spin glasses, and this is how I want to end. So normally you take P as so this is called the P-spin model, and this is one of the favorites of Jorge Corchen. So if one day he looks at the lectures, that's for him. So the cool thing about the P-spin model, there are many cool things, of course, about the P-spin model, but the one cool thing I want to mention today is that it's been studied since the beginning of the 90s. It's been understood initially like 85, 84, something like this. In the beginning of the 90s, the dynamics of this was thoroughly understood, in particular by two of your lecturers, Jorge and Leticia. So they have worked a lot about the dynamics of this. And the one thing I want to say is that the physics of this, of the P-spin model, and the types of phase transition and dynamics that arise in this model, it's the exact same as the mean field theory of the glass transition as obtained by you start from hard spheres, go to large dimensions, solve everything, you get the very same physics all the way. So it's an equivalence between this funny universality class of spin glasses in the mean field limit and the mean field theory of the glass transition. It's the same mean field theory actually, which is why people have spent so much time working at this precise model. So I will stop here and I will do 5 minutes then of equilibrium next time, just to give you a hint of the mean field theory and the key concept that may be useful to when you look at experimental work on tissue. So what about the statics and the dynamics, and what type of calculations you can do with it. So that's how I'm going to start the next lecture, and then we move out of equilibrium quickly.